Hello dear students, let me continue with our discussion on group. So we had started with the group of integers modulo n, that is I had defined something called addition modulo n, right? If you remember, a and b, they are integers and n belongs to natural number. N is a positive integer. Okay. Then what is a plus b modulo n? This is, I told you, this is the remainder when a plus b is divided by n. Okay, divided by n, right? So this always belongs to the set 0, 1, 2 up to n minus 1 by division algorithm. Okay. So we had stated that also, if a and b are integers with b not equal to 0, then there exist unique integers q and r. That is, q is called quotient and r is called remainder, such that a is equal to bq plus r, where this r lies between 0 and n minus 1. Okay. So this is the division algorithm. So a plus b modulo n is the remainder when a plus b is divided by n. Okay, so we will see some important properties which will help us in proving that this group, this set is actually a group with respect to addition modulo n. Okay. Say something like 5 plus 13 modulo 7. Okay, what is that? 5 plus 13 is 18. We have to work out mod 7. Okay, so 18 mod 7 means the remainder when 18 is divided by 7. Okay, so this is another way of writing 18 mod 7. Okay, here it will give us the remainder when 18 is divided by 7. Okay, so what is that? If you divide 18 by 7, the remainder is 4. Okay, because 7 into 2 is equal to 14, and plus 4, that will give you 18. 18 can be written as 7 into 2 plus 4. Okay, like that. So 4 is the remainder, right? So but you see, if we change this modulo, say I change it to 6, 5 plus 13 is 18, so it's 18 mod 6. And what is 18 mod 6? It's actually 0, right? 18, if you divide by 6, the remainder is actually 0. So a lot of thing depends on the number with respect to which you are taking the modulo. Okay. And one more thing that I had told you, if I had told you about congruence. A is congruent to b modulo n, means that a minus b is divisible by n. Okay, this already I had shown you. And by our division algorithm, any number, say if a mod n is equal to r, that means r is the remainder. R is the remainder when a is divided by n. Okay, then what happens? A minus r is always divisible by n. Okay, is divisible by n. Okay, so a is always congruent to r mod n, where r is the remainder. Okay, r is the remainder when a is divided by n. So what we can do is we can reduce very large numbers, okay, say 1573, to small numbers by considering this modulo operations. Okay, say something like mod 5. So if we divide this number by 5, the remainder is actually 3. Okay, so many of the computations, okay, involving these remainders and all can be simplified, okay, by considering this modular arithmetic. Okay, 1573. Suppose I want to find out what is the remainder when 1573 to the power 100 is divided by 5. Okay, so we can reduce it to small number by using this modulo concept. Okay, any number is congruent to its remainder modulo n. Okay, so that way we will see some properties that if we add two numbers, okay, the remainder when this say another number 1873, the remainder when the sum is divided by 5 is same as the remainder when the remainder of this part plus the remainder of this part, and then take the remainder again. Okay, so it gives the same result. Okay, I'll just explain. Okay, just let me. Every time I forget to charge. Okay. So basically, just let us do one result, that a plus b, so a and b are integers and n belongs to natural number, then a plus b mod n. Okay, so that is the remainder when this a plus b is divided by n. This is always same as a mod n plus b mod n, whole thing again taken modulo n. Okay, right. So that means if I add a and b together and then take the remainder, okay, when it is divided by n, this is same as take the remainder of a when divided by n and remainder of b when divided by n, and then add them, and then again take the remainder of the sum when divided by n. Okay, you will get the same result here. Okay, so just let me give you a simple proof so that you can understand this. So we have, so when you divide a by n, we can write a as sum n q1 plus r1. Okay, where this r1 is less than or equal to this 0 less than or equal to r1 less than or equal to n minus 1. Okay, this is the remainder, and b is actually equal to n q2 plus r2. Okay, some other remainder will come for b. 0 less than or equal to r2 less than or equal to n minus 1. Okay, so what is a plus b, or so therefore what is a mod n, means the remainder when a is divided by n is actually r1, right, and b mod n is actually r2. Okay, and what is a plus b? A plus b is actually n into q1 plus q2, this is taken as common, plus r1 plus r2. Okay, this one, right. So see, this r1 and r2, they lie between 0 and n minus 1, but it's not necessary that r1 plus r2 will also lie between these two. Okay, it may happen that the sum crosses n. Okay, so what we can do is we can divide this r1 plus r2 by n again. Okay, and see what is the remainder. Okay, so yeah, so a plus b mod n is not r1 plus r2 directly, because it's after calculated r1 plus r2. Okay, so this part will go because it's n into some number, so this is the quotient part. Okay, and so this part will remain. So a plus b mod n is equal to the remainder when r1 plus r2 is divided by n. Okay, right. Let me explain it again. This part I can write it as n into q1 plus q2, and since r1 plus r2 is again an integer, so if we divide r1 plus r2 by n, again we will get something like n q3 plus say r. Okay, where r lies between, where this r lies between 0 and n minus 1. Okay, so in that case a plus b mod n is exactly r. Okay, so this r is nothing but the remainder when r1 plus r2 is divided by n. Okay, we are not considering this part at all. Okay, we have just considered the division of r1 plus r2 by n. Okay, so therefore a plus b mod n, okay, the remainder when a plus b is divided by n is same as the remainder when r1 plus r2 is divided by n. Okay, and what is r1? r1 is nothing but a mod n. Okay, a mod n means the remainder when a is divided by n, plus r2 is b mod n. Okay, b mod n is the remainder when b is divided by n, and then we add the whole thing, and then again we take modulo n. Okay. So this is basically what I was saying. A plus b mod n is same as a mod n plus b mod n. Then the whole thing again you take mod n. Okay, you are going to get the same result. Okay. So just let me give you one illustration of this result. Say we have something like 53 plus say 72. Okay, I want to find out what is the remainder when we divide this by say 7. Okay, so let me add this to first. Let me add this to 3 plus 2 is 5. 5 plus 7 is 12. So it's 125 mod n mod 7. Okay, so what is 125 mod 7? We have to divide 125 by 7. So if we divide 125 by 7, so it's 7 1 7, then 5 55, 7 what 7 7 are 14, 7 8 are 50, 7 7 are 49. Okay, so this is 6. Okay, so 6 is the remainder. So this remainder is 53 plus 72 mod 7 is 6. Now let us do it separately. What is 53 mod 7 and plus 72 mod 7? Okay, if we do this separately, then what will happen? This will give us 53 mod 7. If you divide 53 by 7, the remainder is actually 49 plus 4. Okay, so it's 4 plus 72. If you divide by 7, the remainder is 7 8 is 56, 7 9 is 63. Okay, so 63 plus 7 10 is 70. So the remainder is 2 actually. Okay, so it's 4 plus 2. Yeah, right. Let me just use a larger number here. Okay, say 74. So it's 4 plus 7. Okay, so that you can understand what is happening. This is 127. So 127, if you divide by 7, the remainder here will be 1. Okay, this remainder is 1. Okay, so this is 1. Okay, so this is 74. So here what I am getting, this remainder is 4. This remainder is, if we divide 74 by 7, remainder is 4. So 4 plus 4 is actually 8. Okay, so see, this is not equal to 1. Okay, but this will be equal to 1 once we take modulo. Okay, here you take the modulo again, modulo 7. Again you take modulo 7. So this will be 4 plus 4 mod 7, that is 8 mod 7. Okay, 8 mod 7 is actually 1. If you divide 8 by 7, the remainder is 1. Okay, so that's basically means if we add this 2 and then take modulus, this is same as taking modulus first, then adding, and then again taking modulus. Okay, so this property we will be using in our this proving the fact that Zn is a group with respect to addition modulo n. Okay, so let us try this exercise. Show that Zn, this is equal to 0 1 2 up to n minus 1. Okay, is a group with respect to addition modulo n. Okay, addition modulo n, right? So let us try it. Let a comma b belongs to Zn. Then we define a plus b modulo n equal to the remainder, means equal to a plus b mod n. So let us write it this way: a plus b mod n. That is what is this? This is actually remainder when a plus b is divided by n. Okay, so by division algorithm, okay, there exist unique integers. So for the closure property, we'll just use the division algorithm so that it's clear. Unique integers q and r, such that a plus b is equal to nq plus r, where what is this r? 0 less than or equal to r less than or equal to n minus 1. Okay, so this r is the remainder. Hence, where r 0 less than or equal to r is less than or equal to n minus 1. So therefore, a plus b modulo n is exactly equal to r, which actually belongs to Zn, because our set Zn is 0, 1 to up to n minus 1. Okay, so therefore, so Zn is closed. Zn is closed with respect to addition modulo n. Okay, Zn is closed with respect to addition modulo n, right? So first part we have done. Next property is I have to verify the associative property. Okay, let a, b, c belongs to Zn. So to verify the associative property, we will use the result that we have just done. Okay. So a, b, c are three numbers in Zn. Okay, so let us see what is a plus b modulo n, then again plus modulo n with c. Okay, so this part will apply the definition. So this is a number in Zn. Already we have seen that if we take two numbers from Zn, then the addition modulo or the sum is inside Zn. So if we apply the definition, it's a plus b modulo n plus c. Okay, this plus is the ordinary plus, and then we take the whole sum modulo n, means we consider the remainder when this sum is divided by n. Okay, that is the definition of this, right? The definition is this: the remainder when a plus b is divided by n. Okay, so we will apply. We have applied this definition. Okay, so this follows by definition, right? So in the next step, again, what I will do, I will apply the definition of this part. Okay, so this is nothing but a plus b modulo n is same as this, the remainder when a plus b is divided by n, plus this c is an element inside Zn only. So c is c also I can write as c mod n. Okay, the remainder when c is divided by n is c itself. Okay, so this c is exactly equal to c mod n. Okay, because c lies between 0 to n minus 1. If you divide c by n, the remainder is c itself. Okay, so something like the remainder when 2 is divided by 3. Remainder when 2 is divided by 3. What is that? If we divide 2 by 3, what is the remainder? Well, it will be, the quotient will be 0. 3 zeros are 0 and remainder is 2. Okay, so that is what. So a plus b mod n. So again, this, the whole thing is taken modulo n. Okay, that means we are finding out remainder here, and then adding these two, and then again finding out the remainder. Okay, but already I had discussed that this entire process is actually same as adding the numbers together, okay, and then taking the modulus. Okay. So this is by property of modular arithmetic, okay, of modulo, okay, modulo addition, okay, by property of modular arithmetic. Okay, so this is, but these are actually integers, so they satisfy the associative property. So a plus b plus c mod n. Okay, so this is by associativity of integers. Associativity of integers. Okay, a, b, c are integers, so they satisfy the associative property. Again, I will apply the reverse process here. Instead of a, I can always write a mod n, okay, plus, instead of b plus c, I will just write b plus c mod n. Okay, yeah, b plus c mod n. Okay, whole thing again taken mod n. Okay, so I have just applied the reverse process here. Here I am adding the numbers and then taking the remainder, but I know that this is same as taking the remainders first and then adding the numbers and then again taking the remainder. Okay, So this is so this part is this part. I'm sorry for the handwriting. So this is this part I can write as a plus a plus b plus c mod n. Okay, this symbol, and then I take modulo n. Okay, but this is nothing but a plus modulo n of b plus modulo n of c. Okay, by definition. Okay, so we have proved the associative property here. Okay, right. So the next one is that is okay. Actually, the question is, I can also write this as is an abelian group. Okay, because it satisfies the commutative property also. We will prove it. Okay, so it's an abelian group. So next thing I have to verify is the existence of additive identity. Okay, so we have the obvious choice is 0. Okay, we have 0 belongs to Zn, and a plus modulo n 0 will be equal to what, and for any a inside Zn, a plus 0 mod n is same as what, a plus 0 means the remainder when a plus 0 is divided by n, right? But what is a plus 0? A plus 0 is a only, so it's a mod n. Okay, but a is an element inside Zn, so a mod n is same as a. Okay, right? Similarly, 0 plus this 0 plus a mod n is actually 0 plus a, is the remainder when 0 plus a is divided by n. This is equal to a mod n. Okay, so a mod n is same as equal to a. Okay, why it is same as a? Since a belongs to Zn. Okay, same as a. Right, here also since a is an element inside Zn. Okay, so the 0 is the identity. Okay, 0 is the identity in Zn. Okay, so we have got the identity element. What else is left in order to declare Zn as a group? That is inverse. Okay, every element should have an inverse. So let a belongs to Zn. So can you guess what is inverse of? Okay, I have to find a number inside Zn which when added to that number gives you 0. Okay, so let me just consider the example of Z4. So it's 0, 1, 2, 3. Okay, so in our earlier lecture we had seen the composition table also. What is the inverse of 2? 2 added with which element will give you 0? Okay, if you see nicely, 2 added with 2 will give us 0, because 2 plus 2 is 4. 4 when divided by 4, the remainder is 0. Okay, what is the inverse of 1? 1 when added with 3 will give us 0. The 1 plus 3 is 4, and when we divide by 4, the remainder is 0. Okay, so from this you are getting an idea that whatever inverse we are considering, the sum has to come to be 0 or 4. Okay, or a multiple of 4. Okay, only then the remainder will be 0. No? If we divide a number by 4, the remainders will be 0 if the number is of this type, 0, 4, 8, 12. Okay, like that. This should be multiple of 4. Okay, so in our if we take one a inside Zn, the inverse should be such an element which when added with a gives you the number n. Okay, so is that possible? So for any number a inside Zn, what about the number n minus a? Okay, if we add a with n minus a, the result that we get is always n. Okay, the result that we are getting is actually n, right? So what we can do is we can easily find out inverse of any element a inside Zn. Okay, so but there is a problem. When a is 0, this n minus 0, it is not a member of this. Okay, so let us do it separately. Let a belongs to Zn. So if a equal to 0, then inverse of 0 is 0 only. Okay, then 0 plus modulo n of 0, this is equal to 0, right? Equal to, yeah, this is equal to 0. So 0 is the inverse of itself. Okay, inverse of itself, right? So let a not equal to 0. Okay, let a not equal to 0, then what we have, 0 is strictly less than, or 1 less than or equal to a less than or equal to n minus 1. Okay, because the set Zn contains only the element 0, 1, 2 up to n minus 1. Okay. So from here, this implies, if I just take n this side, so n minus a, or if I multiply with minus, so minus 1 greater than or equal to minus a greater than or equal to 1 minus n. Okay, I have multiplied both sides by minus 1, and then you add n to both sides, so n minus 1 greater than or equal to n minus a greater than or equal to 1. Okay, so that means I can write 1 less than or equal to n minus a less than or equal to n minus 1. Okay, so this implies n minus a is also an element inside Zn. Okay, also a plus modulo n minus a. Okay, what is that? This is actually a plus n minus a mod n. Okay, mod n. So this is a plus n minus a is n, so it's n mod n. Okay, but what is n mod n? It is actually 0. If we divide n by n, the remainder is actually 0, right? So n minus a is the inverse of a. Okay, right? So every element has inverse, therefore every element of Zn has inverse. Okay, has inverse. So Zn is a group, therefore Zn with respect to addition modulo n is a group. Okay. Next I have to show it's an abelian group. Okay, so now for let a comma b belongs to Zn, okay, be any elements, then a plus b modulo n, this is equal to a plus b. This is very simple. This we can write it as remainder when a plus b is divided by n, but we know a plus b is same as b plus a. Okay, so the b plus a mod n, so this is nothing but b plus a modulo n. Okay, so here I have used commutativity of integers, commutativity of integers. Okay, this is what I have used here, right? Okay, so therefore Zn is actually an abelian group. Zn is an abelian group. Abelian group. Okay, so this is what. So we have proved the group of integers modulo n is actually a group. Okay, so Zn with this is a group with respect to addition. Okay, right? So if in your exam you are asked show that Z5 is a group, okay, is a group with respect to addition modulo 5. Okay, so you can do it in the general way also, or you can do it using composition table. Just the associative property you have to do it this way. Okay, the associative property you just do it this way. So instead of n you will just write mod 5. Okay, if it is Z5, instead of n just write mod 5, and the other things are the same, exactly same. So this identity inverse, everything will be verified from table. Okay, so just let me do one exercise of that type so that you can understand. Show that Z5, so which is equal to 0, 1, 2 up to 3, 4, this is a group with respect to, is an abelian group, abelian group with respect to addition modulo 5. Okay, so solution is we can verify the closure property, then commutative property, and existence of identity and existence of inverse, everything from the table itself. Okay, so that is the advantage if we are given a group Zn with n a given quantity. Okay, where n is a fixed quantity. Okay, then you can verify it from the table only. Just you need to verify the associative property, or you need to justify the associative property using our arguments. Okay, so here a plus b modulo 5, this is actually a plus b mod 5, right? Remainder when. So when you write it in exams, you always make sure that you write it this way, so that somebody else who is using some other symbol for remainder, okay, should not get confused. Okay, so in several books this notation might not be used. Okay, they might write it as remainder when. Okay, so to make sure that you do not fall into the trap of this notations, you write both the notations, a plus b mod 5, and in the next line you write remainder when a plus b is divided by 5. Okay, divided by 5. Okay, so let us we construct the composition table. Okay, we construct the composition table. Okay, so let us do that in the next page. Okay, so we'll construct a table of this type where we'll list these things. So this is 0, this is 1, 2, 3 and 4. Okay, and here also we'll just make some lines. Okay, so this is the operation modulo 5, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay, so 0 plus 0 is 0 when divided by 5, remainder is 0. So in the first row everything will be in its own place, because these are just the remainders, right? 0 plus 3 when divided by 5, the remainder is 3 only. Okay, then here 1 plus 0 is 1, the remainder is 1. 1 plus 1 is 2, remainder is 2. 1 plus 2 is 3, remainder is also 3. 1 plus 3 is 4, remainder is 4. 1 plus 4 is 5, the remainder is 0. Okay, so that way you have to be careful. 2 plus 0, this is 2. 2 plus 1 is 3, remainder is also 3. 2 plus 2 is 4, remainder is 4. 2 plus 3 is 5, remainder is 0. Okay, 2 plus 4 is 6, remainder is 1. Okay, 3 plus 0 is 3, remainder is also 3. 3 plus 1 is 4, remainder is 4. 3 plus 2 is 5, remainder is 0. Okay, 3 plus 3 is 6, remainder is 1. 3 plus 4 is 7, remainder is 2. Okay, 4 plus 0 is 4, remainder is also 4. 4 plus 1 is 5, remainder is 0. 4 plus 2 is 6, remainder is 2. 4 plus 3 is 7, remainder is sorry, I made a mistake here. 4 plus 2 is 6, remainder is 1. Okay, 4 plus 3 is 7, remainder is 2. 4 plus 4 is 8 and remainder is 3. Okay, so that way you have to do the composition table. Okay, so the composition table is done. So from the table you can conclude many things here. So from table we see that Z5 is closed, because whatever numbers we have got inside the table, they are the elements of Z5 only. Okay, closed with respect to addition modulo 5. Okay, then we see that Z5 is closed with respect to addition modulo 5, comma Z5 is commutative, or addition modulo 5 is commutative in Z5. Okay, because this, see, the matrix here is actually symmetric. Okay, so it's commutative. So writing 3 plus 2 is same as writing 2 plus 3. Okay, so if you consider this as diagonal, see, this is all these are matching. Okay, so this is commutative. So plus modulo 5 is commutative in Z5. Then also we see that 0 is the identity. Okay, so we see several things. We see that you may write it as number 1 also. Number 1, number 2, number 3 is 0 is the identity. Okay, in Z5 0 is the identity in Z5. Okay, also number 4 is we'll see the inverses. Okay, inverses of 0, 1, 2, 3, 4 are what? So let us see from the table what are the inverse of 0. 0 inverse is 0 itself. Okay, because 0 plus 0 is 0. For 1, so what you have to do to find inverse? You have to look for the column where you get 0. So here for the row corresponding to 1, the column where we get 0 is the fourth column. Okay, so means the column corresponding to 4. So see, inverse of 1 is 4. Okay, 2, for 2 you see 0 appears here. Inverse of 2 is 3. Okay, so like that we'll mention. Inverses of 0, 1, 2, 3, 4 are 0, 4, 3, 2, 1 respectively. Okay, respectively. So all these are clear from the table itself. Okay, so the last thing that we need to verify is the associativity. Okay, so to verify associativity. Okay, so let A, B, C belongs to Z5, then Z5, then A plus B mod 5 is equal plus B plus mod 5 C. This will be actually, so just like we had verified, this will be A plus B mod 5 plus C, whole thing taken mod 5. Okay, mod 5. This will be again A plus B mod 5 plus, instead of C I can write C mod 5, right? Instead of C it's C mod 5, then again whole mod 5, right? And then I can just write it as A plus B plus C, whole thing mod 5. Okay, by property of modular arithmetic. Okay, by property of modular arithmetic. Right. So again I can write it as A plus B plus C mod 5. Okay, and then this can be written as A plus B plus C mod 5. Okay, or A mod 5 plus B plus C mod 5. Okay, just like we had done actually, A mod 5 plus B plus C mod 5. Okay, then whole thing again taken modulo 5. Okay, so if you just simplify this part, this is equal to A plus B plus C modulo 5, whole thing mod 5. So what is that? This is nothing but A plus modulo 5, B plus modulo 5. Okay, so here we have verified the associative property. Okay, so if you are running out of time and you see that it's difficult to write all these things, just mention one line that we know this addition modulo n is associative, hence this. Okay, just mention that, and hence A plus B modulo 5 plus this is equal to A plus B plus C. Okay, for all A, B, C inside Zn. Okay, it's always better to prove it using this. Okay, but in exam, by chance if you run out of time, okay, and you do not mention this associative property as well, then your marks are going to be deducted. But if you at least mention that we know addition modulo n is associative, therefore this is what happens. So at least the examiner will know that you know what is the associative property. Okay, So we have seen Z5 is a group. So now you can do the same thing for Z3, Z6, Z7, okay, anything, whatever you like. We have already proved the general case, right? Okay, so similar to Zn, there is another group with respect to multiplication. Okay, Z group of integers modulo n with respect to multiplication. Okay, so let me just see what is the notation for this, because if we use the same notation, then it's not going to be a group actually. We have to separate the element 0. ZP, yeah, that is right. That so for that we need P to be prime actually. For multiplication modulo n, okay, we need P to be okay. So let us do it as an exercise. So before that, what is multiplication modulo n? So let us write A cross modulo n, or A into B modulo n. This is what it is, just the product AB taken modulo n. Okay, and that means we have to take the remainder when A into B is divided by n, by n, right? So say something like 5 cross modulo 7 of 12. So 5 12 is 60, so it's 60 mod 7. Okay, so 60 mod 7 is actually 60 modulo 7. If we divide 60 by 7, the remainder is what? 4. 7 is 56. 60 minus 56 is 4. So this is actually equal to 4. Okay, like that. So let us try this. Is Zn or Z5 or say Z4 a group with respect to multiplication modulo 4? Okay. So solution, let us check what is the problem. So in Z4 is what? 0 1 2 3. Okay, so 0 1 2 3, right? Okay. So here, is it a group with respect to multiplication modulo 4? Okay. So you see, if we just construct the table here, multiplication modulo 4, 0 1 2 3. Okay, so this is 0 1 2 3. Okay, so it's 0 into 0 is 0, 0 into 1 is again 0. Okay, 0 into 2 is 0, 0 into 3 is 0. Okay, so from the first row itself, you can see it's not working out, right? 0 into 1, 0 into 0 is also 0, 0 into 1 is also 0. I had told you that in each row the numbers shouldn't repeat. Okay, numbers shouldn't repeat here, right? If it is a group, say 0 into 1 is equal to 0 into 4 of this. Okay, then this actually implies that 1 equal to 2, if at all this is a group. Okay, that is the left cancellation rule. Okay, but here 1 and 2 are unequal, so this is not a group actually, right? So one more thing you can see, if you just multiply 1 into 0 is 0, 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 2 into 0 is again 0, 2 into 1 is 2, 2 to the 4, 0, 2 3 is 6, 2. Okay, see, so here 2 into 0 is also 0. Okay, and yeah, so 1 is an element which satisfies the identity criteria. No? 1 multiplied with any other element gives the element itself. Okay, so for existence of inverse, this the product of two numbers should be equal to 1 actually, but here this is not equal to 1, right? Product is not equal to 1, right? So here there are several problems. So 3 into 0 is 0, 3 into 1 is 3, 3 to the 6, again it's 2, 3 to the 9, again it's 1. Okay. So the problem comes up with the identity. Okay, which element you will take as identity. Okay, the which element has inverse, which element doesn't have inverse. Okay, so the problem comes up with this, right? Okay, so let us write it nicely, justify it nicely. So Z4 is not a group. Here 1 belongs to Z4 is satisfies all properties, or satisfies the criterion for identity element. Okay, for being identity. Okay, as 1 into this A is equal to 1 into A mod 4, right? Mod 4. So 1 into A is A only, so it's A mod 4. So this is equal to A for all A inside Z4. Okay, so 1 is the identity. Okay, but 0 belongs to Z4, does not have inverse. Okay, doesn't have inverse, as 0 multiplied with any other element is 0 only. It is not equal to 1. Okay, right? 0 multiplied with any other element is 0. So 0 belongs to Z4, doesn't have inverse, as 0 multiplied with any other element of this, as 0 multiplied with this is equal to 0 for all A inside Z4. Okay, so which is not equal to 1, right? And 0 is not equal to 1, which is not equal to 1, right? So 0 doesn't have means we cannot find an element A which when multiplied with 0 gives you the identity element. Okay, which is not equal to 1, the identity in Z4. Okay, so Z4 has identity. There is an element which when multiplied with every other element gives you the identity element. Okay, so but there are elements which do not have inverse. So 0 doesn't have inverse, in Z4. Okay, so 0 is creating the problem. So let us try this. So is this group A equal to 1, 2, 3, 4 a group with respect to multiplication modulo 4? Is this a group with respect to multiplication modulo 4? So here also you see this identity element is 1. Okay, 1 multiplied with any other things is 1. So 1 is the identity, but you see there are several elements which do not have any inverse, because 2 into 2, but 2 belongs to A, doesn't have inverse. Okay, not only inverse, means it doesn't satisfy closure property only. Okay, A is identity. Okay, identity is there, but A is not closed. Okay, A is not closed. Okay, closed with respect to multiplication modulo 4. Why? Because you see 2 into 2 mod 4 is what? 2 into 2 mod 4 is 4 mod 4. So this is 2 to the 4 when divided by 4, the remainder is 0. Okay, so 0 which doesn't belong to A. Okay, so it's not A itself, it's not closed itself. Okay, so in general, if we take the integers 1 to up to n, okay, or 1 to up to n minus 1, it might not be a group with respect to multiplication modulo n. Okay, in general it's not true. So in general this set 1 2 up to n minus 1 is not a group with respect to multiplication modulo n. Okay, but there are certain cases, where it becomes a group. Okay, where it is a group. It is a group. Okay, in particular when, okay, so we'll see in particular when n is a prime number. When n is prime, it becomes a group. Okay. Prime, it becomes a group. Right. So that particular group usually is denoted by ZP, where P is prime. ZP where P is, that is ZP where P is prime. P is prime is a group with respect to multiplication modulo n. Okay. Multiplication modulo P. Okay. Multiplication modulo P. Okay. Right. For example, you try this one exercise and try this. Z3 equal to, so unfortunately the same notation used for both, so the operation matters actually. Z3 equal to 1 2. Okay, this is a group with respect to multiplication modulo 3. Okay, so you can try it this way. Okay, so as of now we have done almost all examples of group which were listed in syllabus. So in the next class I can start with okay, I'll do something about this ZP if that is required, and in the next class I'll start with the second unit, that is the properties, subgroups and all. Okay, the other properties of groups. Right. Thank you.